Hello everyone. So now I'm going to talk about some physics, actually, and we'll be able to use some basic gravitational rules in Newtonian physics, keeping track of position, velocity, and acceleration, to create a solar system animation. And just from the specification of a planet's mass, its distance to the sun, and its speed, we'll be able to use the laws of gravitation to simulate their orbits. And from that, we'll actually be able to calculate how long a day is on that planet. And so there's a connection here between the last assignment on leap years. This is one way that we can actually estimate how long an average year is on the Earth in number of days. Now, in the background, the purpose of this assignment really is to practice loops, and in particular nested loops, so a loop within a loop. But I hope this will be a fun application, and it'll be thought-provoking and maybe inspire some people for their final projects. All right. But let's start with a much simpler example, and then you'll do a fancier example in your homework. But let's just start with the Earth and the Moon, and that'll be enough for me to illustrate all the concepts about the animation and about the physics. Okay. So this will be a so-called two-body problem rather than an n-body problem, because there's only going to be two celestial bodies interacting with each other. So before I dive completely into it, let me first define something called the gravitational constant. So I'll say big G is equal to 6.67408 times 10 to the negative 11. So this is scientific notation, that's what that means. 6.6748 times 10 to the negative 11. And the units here are meters cubed per kilograms times seconds squared. And just a little bit of intuition here. So what is this gravitational constant? Well, it basically tells us how strong the force is going to be between two bodies that have mass based on how far away they are. So that's why you see the mass here. So it's the kilogram, and then the distance here. It's a function of the distance that the bodies are apart. And what it gives you back is a per second squared. And if you've seen any physics before, you know that's an acceleration. Okay? So from a mass and a distance between two bodies, we will be able to determine the acceleration due to gravity between those two bodies. All right, so that's like, these are the knobs that the universe has turned for us. If you change this number, then the gravitation would change, but this is what we estimate it to be, roughly. Now let's set up the data for the Earth and Moon. So that's really our first step here. So first of all, the Earth and the Moon we're going to represent as sphere objects, and if you remember from class, these are objects that come along with this nice VPython library. It'll be able to draw the sphere for us at a particular position. What I'll do is I'll be a very self-centered human, and I will say, okay, well, the Earth is at the center of my coordinate system. We are very self-centered. And so it's x position 0, it's y position 0, it's z position 0. So in VPython, we use these objects called vectors, which are really just lists or arrays of 3 elements. And the reason there is because we're in 3 dimensions, so we have 3 coordinates, x, y, and z. Okay? So the position is specified with 3 coordinates. We can also specify the radius of the sphere. So the radius of the Earth is 6 times 10 to the 7th meters. So that is 60 million meters. Pretty big. And then we can also set a color. And the way colors work is, I think I'm going to mention this, a color is made up of a red, green, and a blue channel. That's the way we represent colors. And so actually this has got to be a vector as well in VPython. It's also a list of 3 elements. The first one is the red channel. Now it's the Earth, so I want it to be blue-greenish. So I'll say, okay, no red, but so R red, G green, that's the next one. I'll do a little bit of green, so 0 is nothing, 1 is all, as much as I could put into that color channel. So I'll do a little bit of green, and I'll do a little bit more blue, okay? So no red, a little bit of green, a little more blue, and that's our Earth. Now before I do anything else, let me go ahead and run this, and I see my Earth. Okay, so that's my Earth to start with. There's one more piece of information I should know about the Earth, which is its mass. So the mass of the Earth is 5.974 times 10 to the 24th kilograms. So that's pretty huge. It's a little bit heavy. You'd have a hard time lifting it probably. Maybe you could work your way up to it, but for now, that's probably beyond our reach. Okay. But I guess Atlas could do it, right? Okay, so 5.974 times 10 to the 24th kilograms. All right, great. So let's set up now the moon, which is also its own sphere. So let me just do that thing where I'm going to copy and paste some code, but be very, very careful and change the appropriate thing. So the moon, I'm going to start off pretty far from the Earth. It's going to be 384.4 million meters away. Okay, let me make sure I got that right. It was 384.4 million. So we got our 1,000 million meters away. Okay, that's not that far. The radius is actually about a sixth of the radius of the Earth. And the color is gray, and so it turns out if the amount of red, the amount of green, and the amount of blue is the same, then we perceive that to be gray. So I'll just make them each halfway. All right, so let me go ahead and check this again and see what I see. And I look here, and there we go. I see the moon over there, and there's my Earth still. Okay, very nice. Okay, so let me now set up the velocity of the Earth, or sorry, the velocity of the moon. I forgot to change this to be called moon. But I'll set up a vector called the velocity. And so I'll say the moon is going 1,000 meters per second. Okay, now what's interesting about this is I actually have 3 numbers for the velocity of the moon. And that's because I can move in any of 3 axes directions. We start off moving fully in z at 1,000 meters per second, but that'll actually change a little bit over time. Okay. All right, so let's keep going here. So that was step 1. Step 2 is going to be to create the animation and apply the laws of physics. Okay, so I think we have all the information that we need. So yeah, we need to know the mass of the Earth, we need to know the velocity of the moon, and we need to know the relative positions next to each other. Okay, so I'm going to do something like I did in class, and I'm going to keep track of the time that elapsed at each step. So I'll say last time is equal to time.time. You remember that's the number of seconds that's elapsed since January 1st, 1970 at midnight. But we can use the difference between the time at one animation frame and a time at the next animation frame to keep track of the elapsed time between the frames. So that's what we'll do. I'll also keep track of the total elapsed time because I want to eventually stop the simulation. So I'll say it's 0 to begin with, but this will accumulate the amount of time that's elapsed over each frame. There's actually one more thing I want to do. If I were to do this simulation real time using all these constants, we would be waiting a month for the moon to go around the Earth once. So let's not do that. Instead, what I'll do is I'll speed it up a little bit. So let me define a variable called seconds a day, and I'll say, okay, let's say there's 24 hours in a day, 60 minutes for every hour, and then 60 seconds for every minute. So that's how many seconds there are in a day. And what I'll do is I'll make it so that make the simulation elapse by 1 day every frame, rather than real time. Okay. Or what I'll do, I guess what I'm saying is I'll let the animation go as fast as it can, but I will speed up the physics by a factor of a day. So if a tenth of a second elapses, then I'll make a tenth of a day elapse. That will be my plan. Okay. And so what I'll do is I'll let this simulation go as long as we are less than 60 days. All right, so we should see like roughly 2 revolutions of the moon around the Earth. Okay, now you remember, the first step that we do in the animation loop is compute the elapsed time since the last frame. So first what I got to do is I'll set up a variable for the current time, and then I'll compute the elapsed time as the current time minus what the last time was, and then I'll remember what this time was for the next frame. That's a very standard thing to do, to keep track of the elapsed time. Now if you recall, the next thing we have to do, this is the real meat of the work here, is apply physics. Okay? And so what I need to do first is actually set up an arrow from the moon to the Earth. Okay, so if I do the following, I can actually do this vector subtraction here. And normally I would take a lot more time to explain this. I usually take a few classes to explain this in my graphics class. But for now, let's just roll with it. I can create an arrow from the moon to the Earth, which that's the arrow that gravity would be applied, right, from the moon's perspective. So the moon's getting pulled towards the Earth. I can do that by saying it's the Earth's position minus the moon's position. Okay, now at this point, I've written more than enough code. I should stop. I'm not finished, but I've written a lot of stuff. Let's just make sure I didn't make any syntax errors, okay? I highly encourage you to check your code as early and often as you're going along. So I'm running this again, and I don't see any problems. So that's good. Nothing exciting is happening, but it doesn't appear that I made any syntax errors. Okay, great. So we are at the stage where I had figured out this arrow. From that arrow, I can also compute the length of the arrow, which is the distance from the Earth to the moon. And to do that, I can say, I'll call it r, and that's arrow.mag. So distance is also referred to as the magnitude of the arrow. So this is the distance from the Earth to the moon, and it starts out as being this very large number, 384.4 million meters. All right, so that's what the distance starts off at. And from that distance, we can actually compute the acceleration. So the acceleration due to gravity, using the gravitational constant that I defined here, using the mass of the Earth, and then using the distance from the Earth to the moon. And so it turns out that acceleration vector can be computed as the direction, or the arrow, times the gravitational constant times the Earth mass over that distance cubed. Okay, so that's why we see these particular units here: meters squared, kilograms, or sorry, meters cubed, kilograms, and seconds squared. So the units of this will be seconds squared, or per second squared. So those are the units of acceleration. Okay, now we apply something called an Euler step. So what we can do is, from the acceleration, compute the elapsed time, or sorry, compute the change in velocity based on the acceleration and the elapsed time. Now I told you I wanted to speed up the elapsed time, so let me do that real quick. Let's multiply this elapsed time by the number of seconds in a day, so that this animation goes a little faster. Okay, now the rules are for this Euler step. What we say is, okay, the velocity is what it was before, plus the acceleration times the elapsed time. And then we say that the position, so I'll say the moon.position is what it was before, plus the velocity times the change in time. So there's this little cascade here. I update the velocity based on the acceleration, which was determined by gravity. So the acceleration is wanting to move the moon back towards the Earth. The moon is trying to go its own way, but the acceleration is pulling it back, and so it'll end up going in this orbit. And so from the acceleration, I can pull the velocity back a little bit, and then I can update the position, so actually move along that direction. So that should be it. Let's see, did it work? No, not yet. Let's see. Do we see anything in the console here? No, I didn't. Maybe I just need to close this and launch it again. I think that's it. Let's try. So it said keyboard interrupt. When I closed the window, it stopped that program. Let's try to run this again. And I see an orbit. Nice. So one thing that might help me a little bit is I can put, you don't have to do this in the assignment, but just to show you, I can put a little bit of information to be displayed on top of the moon here that kind of follows the moon. I wrote this ahead of time because this is a bit tedious, but let me paste this in here real quick. If I put this code here, and then, so this is a label, it's going to track the position of the moon, and I have some information about the font and things. And then what I can do is I can actually say, okay, well, how many days have elapsed? So within this loop, so this is really, the animation part happens, right? So, and then we update graphics, which this kind of step is actually both physics and updating graphics. This is going to update the position, but we can also update this little label that we had. So I can say this little label L.text is equal to, well, however many days went by. So I'll say, okay, up to 3 decimal point precision, let's output the number of days that went by. And that would be the total time elapsed. Oh, actually I forgot to, okay, this is in an infinite loop right now because I forgot to accumulate the time as it went by. So actually, I want to make sure that I add on to total time the elapsed time in this frame. So this will actually accumulate the time now, and then this loop should eventually end. But I can also display that total time here on the label. And I think that's all I need. Okay, so anyway, again, I added a label that's going to be attached to the moon. I've accumulated the time as it's changed. So every frame, I add on the amount of time that's elapsed in this frame to the total time elapsed. And then I output that information to the animation. Okay, so let's have a look at this. Oops, looks like I made a mistake. I forgot to divide by... Okay, so I had sped up this time by the number of seconds in a day. So I better divide that by the number of seconds in a day if I'm going to accurately display the number of days. Okay. All right, let's try it again. Okay, cool. So here's what the animation is showing now. So if I watch this moon go around, so it started around there. Somehow it's not actually tracking the position of the moon. That's interesting. But anyway, at least we can see where it started. Look back in the code here, see if I missed anything. But anyway, yeah, we see, in roughly 30-ish days, it went around. So that's cool. This seems to be accurate. Let me see if I can just fix that label real quick. Oh, I think I have to update the position of the label as well. So I have to say, okay, the position of the label is equal to the position of the moon. Let's try that. Okay, now this actually moves along with the moon, so that's kind of cool. The moon can speak for itself. So there we have it. The moon going around the Earth. And so you'll do very similar things in the assignment. The only difference is it's not just one planet that's acting on a moon, it's actually all the planets acting on each other. So instead of just computing one acceleration like this, you will accumulate accelerations from all the planets. So you say, okay, the sun causes this amount of acceleration. To that, and actually the sun is the most massive thing, so that's going to be pulling me the most. But the planets will also pull in each other a little bit. So for the Earth, like I would add on the acceleration for the sun, but then I would also add on the acceleration for Mercury, and then I would add on the acceleration for Venus, and then I would add on the acceleration for Mars, because they all actually pull in the Earth a little bit too. So that's what you'll do in the assignment, but basically it's very similar to this. Okay, so I'll provide this code, and we'll workshop it in class, and we'll resolve any questions that come up. Okay, so I hope you enjoy this. I hope this is eye-opening, and I hope this is a cool application of loops. Okay, talk to you soon.